The second type of temperature sensors are by using thermistors or thermal resistors. And there are two types of, at first, these are also resistors. They're called thermal resistors, and these resistors use different materials. They typically use ceramic materials based on sintered, semiconductor oxides. These are semiconductors. And there are two types of thermistors, NTC and PTC, negative coefficient, negative temperature coefficient, and positive temperature coefficient. That means, for NTC, its resistance decreases with temperature, and, for PTC, their resistance increases with temperature. So the relationship is exponential. R over R naught equals E to B times 1 over T minus 1 over T naught. So B here is called the B value. It's sometimes we call it thermistor value. This is, the coefficient of response. Then we have T. For T, T is in Kelvin here. So it's exponential. That means we are going to get large response. That's good. We are going to get a large signal. So just to show you a few cases of, resistors. So on the left here, I'm showing you NTC. This is a negative temperature coefficient resistors. And you will see, this NTC is made by nickel oxide. Nickel oxide is the NTC material. We have two nickel electrodes connecting the nickel oxide material in the middle. So in the middle, we have NTC material. So as you increase your temperature from 20 to 70, you will see its resistance decreases from 1 to almost 0. And you will see the rate of change is about 9% per degree C, which is pretty large. So if you compare that with, nickel, which is a metal, which is, RTD material, is about 0.5%, as we just mentioned. So NTCs have large response. And there's also a PTC material. So, for this particular one, as temperature increases from 25 to 35 degrees C, the resistivity goes up by about 6 orders of magnitude, which is huge. Okay, so, but why, but how does NTC work? So, for NTCs, they are semiconductors, their resistance decrease with temperature. Why is that? Why does the resistance of semiconductors decrease with temperature? Okay.
Is that more like there's more energy to get through the band gap? Nuts.
Yeah, because in semiconductors, the electrons are, partially, free. They need to be activated by thermal energy. So with high temperature, more electrons holes get excited. So, then there's more charge carriers. So the resistance decreases. That's NTC. And for PTC, it's a completely different mechanism. It's based on something called phase transition. So we are not going to talk about that. Okay. And luckily we don't need to microfabricate our own thermistors. We have off-the-shelf thermistors that we can buy. Okay, so I'm showing a picture of a component here. So what is this component? If you have ever soldered, what is this component? Where you see this?
Looks like a transistor.
Looks like a transistor. It's a two-terminal device. Okay, so you will see this in your lab 5. So this is a resistor. So when you see a tiny component, a tiny black component, it is most likely a resistor. So if you look into this resistor, you will see it has two electrodes, and they are interdigitated electrodes, and the bulk is the semiconductor ceramics. This is the NTC material. We are going to use this type of NTC for our thermal sensing and From the data sheet, we can see is, response to temperature as we go from -40 to 150 degrees C, its resistance decreases by like, 3 orders of magnitude. This looks large, but, in wearables, our temperature range is really very narrow. It's, typically about like, let's say 30 to 40 degrees C. It's a very narrow range. So if you look at this graph, it's really just a very small range within this graph. So in your sensors, you will just likely see, a resistance change about like 10 or 20%. That's it, because our temperature range is limited in wearable applications. And the third type of, temperature sensors is IC chips. So for example, so our BLE chip, the BLE chip we are using has a built-in temperature sensor. It has a, resolution of 0.25 degrees C. There are also dedicated temperature sensing chips